Welcome, fellow travelers, to the captivating world of chemistry. Today we embark on a journey to explore the fundamental forces that govern the interactions between atoms and molecules. Prepare to unravel the mysteries of electronegativity, a concept as fundamental to chemistry as gravity is to the cosmos. Imagine atoms as tiny universes, each with a nucleus at its core, orbited by electrons like planets around a star. Just as gravity dictates the celestial dance of planets, electronegativity governs the attraction between atoms in the realm of molecules. Understanding electronegativity unlocks a treasure trove of chemical knowledge. It allows us to predict how atoms will bond, the properties of the resulting molecules, and even how substances interact in solutions. Let's begin our exploration by delving into the heart of electronegativity and uncovering its secrets. In the simplest of terms, electronegativity is an atom's inherent desire for electrons. Think of it as an atom's electron greed. Some atoms possess a stronger pull on electrons than others, much like a cosmic vacuum cleaner with varying levels of suction power. This attractive force originates from the structure of the atom itself. The number of protons in an atom's nucleus, its positive charge center, plays a crucial role. More protons exert a stronger pull on the negatively charged electrons. Electronegativity is a relative property, meaning we measure an atom's electron hunger compared to other atoms. We use a scale, developed by the brilliant chemist Linus Pauling, to quantify this atomic tug-of-war. Now that we've grasped the essence of electronegativity, let's see how it helps us understand the different types of chemical bonds that hold atoms together. Atoms rarely exist in isolation. They are social creatures, constantly seeking to form bonds with each other. This is where electronegativity comes into play, dictating the nature of these atomic partnerships. When atoms with similar electronegativity values bond, they share electrons relatively equally. This balanced sharing results in a nonpolar covalent bond. Think of it as an amicable agreement where both atoms contribute and share resources fairly. However, when atoms with significantly different electronegativity values bond, things get a little more interesting. The more electronegative atom exerts a stronger pull on the shared electrons, creating an unequal distribution of charge. This results in a polar covalent bond, where one end of the bond becomes slightly negative, and the other slightly positive. In extreme cases, when the electronegativity difference is vast, the more electronegative atom can completely snatch an electron from its less fortunate partner. This creates ions, charged atoms, and results in an ionic bond, held together by the electrostatic attraction between opposite charges. To determine the type of bond formed, we need a way to quantify the difference in electronegativity between the bonding atoms. That's where the electronegativity formula comes in handy. Fear not, fellow explorers, for the electronegativity formula is not a mathematical monster. It's a simple tool that helps us predict bond types based on electronegativity differences. Here's the gist. We calculate the absolute difference, meaning we ignore any negative signs, between the electronegativity values of the two atoms involved in the bond. We can find these values on the Pauling electronegativity scale, Den equals sign En1, En2 where Den represents the electronegativity difference. En1 is the electronegativity of the first atom. En2 is the electronegativity of the second atom. The resulting value gives us a clue about the type of bond a Den less than 0.5- nonpolar covalent bond, electrons shared equally, 0.5 to less than 1.7- polar covalent bond, electrons shared unequally, Den greater than or equal to 1.7- ionic bond, electrons transferred, creating ions. This formula provides a handy roadmap for navigating the world of chemical bonds. Let's put it to the test with some real-world examples. Section 5, Examples in Action, from water's dance to salt's embrace. Let's start with water, the elixir of life. Oxygen's electronegativity is 3.44, while hydrogen's is 2.20. The difference is 1.24, placing the OH bond firmly in the polar covalent category. This polarity gives water its unique properties, like its ability to dissolve many substances. Next, consider table salt sodium chloride. Sodium with an electronegativity of 0.93 and chlorine with an electronegativity of 3.16 have a whopping electronegativity difference of 2.23. This indicates an ionic bond where sodium readily donates an electron to chlorine, forming Na plus and Cl ions held together by electrostatic attraction. Finally, let's examine the bond between two chlorine atoms in a chlorine molecule. Since both atoms have the same electronegativity of 3.16, the difference is 0. This signifies a perfectly non-polar covalent bond, with electrons shared equally between the two chlorine atoms. These examples illustrate how electronegativity differences translate into different bond types, influencing the properties of the resulting molecules. But our journey doesn't end there. Let's now dive into the fascinating world of solubility and see how electronegativity plays a crucial role in this phenomenon. Section 6. The mystery of mixing diving into solubility. Imagine stirring a spoonful of sugar into your morning coffee. The sugar crystals seemingly vanish, becoming invisible within the dark liquid. This everyday act of dissolving is a fascinating chemical process driven by the interplay of forces between molecules. Solubility refers to the ability of one substance, the solute, to dissolve in another substance, the solvent, forming a homogeneous mixture called a solution. But why do some substances readily dissolve in certain liquids while others stubbornly refuse to mix? The answer lies in the intricate dance of intermolecular forces, with electronegativity playing a starring role. Understanding solubility is crucial in countless applications, from developing medicines that dissolve in our bodies to creating cleaning products that effectively remove dirt and grime. So, let's explore how electronegativity governs this essential chemical phenomenon. Section 7. Like dissolves like. Electronegativity and the art of dissolution. The golden rule of solubility is like dissolves like. This means polar substances tend to dissolve well in other polar substances, while nonpolar substances prefer to mix with their nonpolar counterparts. Electronegativity holds the key to understanding this principle. Polar molecules, with their uneven charge distribution due to electronegativity differences, can interact favorably with other polar molecules. For instance, the slightly positive hydrogen end of a water molecule is attracted to the slightly negative oxygen end of another water molecule, forming hydrogen bonds. These strong attractions allow water to dissolve polar solutes like sugar or salt. On the other hand, nonpolar molecules lack this charge separation and interact weakly through temporary fluctuations in electron distribution. They are not easily integrated into the structured network of polar molecules like water. This is why oil, a nonpolar substance, doesn't mix with water but readily dissolves in nonpolar solvents like gasoline. Understanding the interplay between polarity and electronegativity helps us predict and explain solubility phenomena in various chemical and biological systems. Section 8. Everyday encounters. From sugary delights to soap's cleaning power. The concepts of electronegativity and solubility are not confined to textbooks and laboratories. We encounter them constantly in our daily lives. That spoonful of sugar dissolving in your coffee or tea, a prime example of a polar solute. Sugar, dissolving in a polar solvent, water, due to favorable interactions between their slightly charged ends. Now think about washing your hands with soap. Soap molecules are fascinating because they have both polar and nonpolar regions. The polar head, with its charged groups, readily interacts with water, while the long nonpolar tail interacts with greasy dirt and grime. This dual nature allows soap to effectively trap grease and wash it away with water. Even the air we breathe and the medications we take rely on the principles of electronegativity and solubility. The oxygen we need to survive dissolves in our blood, a polar solvent, while many drugs are designed with specific polarities to target particular areas of the body. These everyday examples highlight the profound impact of electronegativity and solubility on our lives. Section 9. Unlocking the secrets electronegativity and solubility in review. As we conclude our journey into the realm of atoms and molecules, let's recap the key takeaways. Electronegativity measures an atom's ability to attract electrons in a chemical bond. Electronegativity differences determine bond types, nonpolar covalent, polar covalent, or ionic, like dissolves like. Polar substances dissolve best in polar solvents, while nonpolar substances prefer nonpolar solvents. Electronegativity plays a crucial role in solubility by influencing the polarity of molecules and their ability to interact with each other. Understanding electronegativity and its impact on solubility unveils a deeper understanding of the world around us, from the properties of substances to the intricate processes of life itself. Keep questioning, keep exploring, and keep marveling at the wonders of chemistry.